So thank you for the introduction, and thank you for the invitation to talk about my research. So when I got the invitation, I felt like I need to talk about something that you don't get to hear much on a regular basis. So among many of the communication projects that I have, I chose just two which are related to radio astronomy. So I'm hoping that all of you don't work as much in radio astronomy and how they work. So that's why I chose this. Just to give a brief background, I think all of you have some familiarity with communication systems, right? Okay.
Yes.
Okay. So this is a bit different because now we are going to look at coexistence issues. So if you look at spectrum, this is the FCC spectrum chart. I'm pretty sure all of you have seen in different formats many times. What we see here is the allocation for different users. Allocation of frequency that are for particular users. Sometimes they can be protected, sometimes they are unlicensed, sometimes they are unlicensed. There are so many rules to this spectrum. However, the spectrum is a constant resource. It's a constant electromagnetic resource defined by frequencies. And we cannot have more than what we already know that we have. So in this case, you can see a lot of different colors, and they are for different users. In a large scale, we can try to separate these users into two parts. One is active, the other one is passive. Active is basically where you have the transmitter actually present, transmitting communication. We all use phones, mobile phones that actually transmits and receives signal from base stations. GPS, we all use GPS. Radar, all of these are active transmitters. Passive usage we talk less about, but passive usage are the ones where there is no transmitter. So no human-made transmitter transmitting modulated signals. The two examples are remote sensing and radio telescope, or the radio telescope that is used for radio astronomy. So they're still measuring electromagnetic spectrum and the signals, but not man-made or human-made signals. They are measuring the signals that are coming either from the Earth, and here is one example for that, or they're measuring signals that are coming from far away cosmic bodies, and that's what they're measuring. So naturally, these signals, and I will talk mostly about the radio astronomy because that's where the fundamental work that goes in, but some of the work can actually be used for remote sensing as well, although we haven't done that yet. So one of the important parts to understand is the radio astronomy, how it works. So radio astronomy observes signals from very distant astronomical objects, which means that as the signal is propagating all the way to Earth and we are observing from Earth, the signal has attenuated significantly. So if we want to measure a signal using a software-defined radio, a USRP, a radio astronomy signal, we won't get anything. So that's one of the important parameters to understand, that these signals that are coming from outer space, their emissions are measured in Janskys. And Jansky was the radio astronomer, the most famous one. And he gave us this equation, which is 10 raised to the power of -26 watt per meter squared per hertz. So that's the lowest value, that's the low value that it is measured. How do we measure this? We use really large dish antennas. So the dish antennas are very directional. They focus the signal to the feed. So that's how we get better signal quality. We also have to do long integration times to actually see some signal, if it is astronomical or not. In some cases, we also need to do larger bandwidth integration to get anything which is an astronomical signal. So one of the other parts is, if we look back at some of these, there are yellow regions that are protected for radio astronomy. Now, in that area or in that frequency, there are no other transmissions going on. And if that is the case, then why do we need to think about coexistence and issues and other things? The issue is that the radio astronomy needs to transmit in or receive in wider spectrum, wider than what it has been allocated, for two reasons. One is redshifting of the signals. That happens when the cosmic objects move, and due to expansion of our universe, the signals shift in frequency, and that is called a redshifting. Also, there are some signals which are wideband in general, so those we need to observe the electromagnetic spectrum in a wider band than what is provided as the protected band for radio astronomy. So here is one example where, due to redshift, the H1 line, and I will talk more about H1 line because that's the most prominent line showing up in 1420 megahertz. That is due to our universe. So that's a very known signal that we know. And it is the most prominent one, I would say, coming from Milky Way. So the rest frequency is 1420, and you can see that here it has moved. Both LMC and SMC has moved due to the shifting. The other example is over here, where again, this is the protected band that is given, and the dotted line is just showing the protected band. But this is time and frequency, and these are the radio bursts, fast radio bursts, or FRBs, that has been captured by DSA 110, which is an antenna array for radio telescopes. And as you can see in all of these examples, at different times of day, different days, it is observed beyond this dotted line. So the FRBs are observed beyond this protected region. So there is a need from radio astronomy side to observe in a wider band. However, wider band creates more issues, because wider band means they have to live with other communication, because over here they are now trying to look at other regions where there are other communication might be happening. So how is it done? So first thing is, when there are other communication signals that come in, we call that as RFI. RFI is radio frequency interference, and in general, we can say that RFI is the signal which is any RF signal that is not of interest, and the signal of interest is the astronomical signal. So any kind of out-of-band emission from our communication system, so the base station is transmitting and its harmonic might show up in some other part of the frequency. If we are actually doing communication, it might not matter because the amplitude is so low, but for radio astronomy, it does. It can be even generated from the telescope instruments that is actually measuring. So their instruments are super expensive. Also, there could be presence of other signals outside the protected band. And to just remember that radio astronomy services, or RAS, has been allocated only 1 to 2% of spectrum under 50 gigahertz, where most of these are observed. So how do they deal with it? So first way is, or the current methods is, because if you have RFI, basically you cannot do much with it. You are going to lose time in your radio telescope, in your observations. So some spatial filtering can be done. If we know, oh, it is coming from this side, so we can do some spatial filtering. But the most common thing that we do is statistical analysis of the received signal of the full bandwidth. And then we try to understand, oh, there is some similarity here. There is some cyclostationary property there. So let me try to get rid of those signals. And those are flagged and discarded, and then the rest is used. One of the issues by doing that is we are losing the signal. There is a significant loss of data to reconstruct the signal back, and it reduces the sensitivity of the telescope because now we need longer time frame because of this loss of data to get the same sensitivity. So in general, another main problem that can also happen is this is the signal that is captured. And you can see over here, this part is actually the hydrogen line, which might not be very visible in this capture, but still it's there. And these are different other RFI that are showing up. And it is much broader than the protected frequency or protected zone. So if we do all the techniques for statistical analysis and flagging, all the recent methods, we will end up with this. What this means is the yellow ones are marked, the yellow bins are marked to be incorrect, and they are all yellow, and they are taken off from the data. So the rest of this part is used for reconstruction of whatever we want to reconstruct it back. Now, the most interesting part is after we pass this, and we can see that the actual hydrogen line that was there, that got removed and marked yellow because we are just doing statistical filtering. So that causes other issues for radio astronomy. So it's not very provable system. So that's when we say that we can do two different types of methods. The first one is coexistence with collaboration. So what we suggested is that this is the figure where we have a bunch of transmissions happening. This is the base station. This is another base station. And then let's try to focus on the base station first. There could be many options or many sources of transmissions or RFI, but base station is the most problematic one for the radio astronomy. But if we think about this, that this is a base station, it has its footprint over here, it has its footprint over here, but the signal doesn't stop propagating. It's because we are unable to capture the signals with the device that we have. So it propagates all the way to the radio telescope, which shows up as RFI. And that's when the radio telescope is looking at a signal coming from space, and the RFI is interfering, and that's where you will see the issues showing up, which is mostly related to coexistence issues. We cannot coexist. So in this case, what we suggested to do is we will decompose the signal at the base station. Then that decomposed signal will be sent over internet to the radio telescope. And then the radio telescope also receives the RFI and the signal space, and at the telescope, we will do some calculations, some processing to separate the signal and then cancel the RFI and then retrieve the actual signal of interest from the space. So that's the overall goal, and we are still working on this project, but I would say that we have done some parts of validation at OVRO which are still not out there. We are still working on that. So what is OVRO? OVRO is Owens Valley Radio Observatory. This is in California. And these are the DSA 110 antennas. And as you can see that this is another antenna, but that is much farther out, much larger. These are smaller size dishes, 4.65 meters. So not very small, but pretty small compared to the large dishes that you can think of when you think of radio astronomy. So we use our more array techniques, and these are the actual locations of the antenna. So a lot of array techniques are used to get the signal strength higher than using a really large dish. So we captured a bunch of signals from this setup, and we use that for our experiments. So first thing is, let's take a look at how the temporally and spectrally the signal will look like. So H1 line is the most prominent line, radio astronomical signal. So we captured this signal from over the air using the radio telescopes. Okay, so and then this is something that we synthetically generate. We transmit over synthetic channels and attenuators, filters, all of those, and then we add them up. And if we do that, this is what we get as composite signal, and this is what we get in frequency domain. Now, why we don't actually transmit signal, and instead of actually transmitting signal, we are using a synthetic one? Because 1420 megahertz is a protected band. It's not just license that someone can give experimental license to us. This is a protected band, so no transmission is allowed in that protected band. So that's one of the reasons, if we really want to do a superposition of two signals, one can be captured truly from the radio telescope antennas. The other one is synthetically generated. And that's what we have to start with. Oops. Okay, so I wouldn't go into the details of how we did the cancellation, but our first work was using DSP-based mechanism, digital signal processing-based mechanism, where we first did Karhunen law transform to basically decompose the baseband signal, and that baseband signal, once decomposed, is shared with the telescope. And after that, the telescope also decomposes its composite signal, because the telescope actually receives this signal, this is the signal that the base station is transmitting, and this is what it is received at the telescope. And then we do an orthogonal projection of those two so that we can cancel out the RFI, and then we reconstruct the astronomical signal back using inverse KLT method. This is the one figure that actually shows what we have done. And there are more figures in other papers, but essentially the composite signal looks like this, which is the yellow line, where you can see that there is a tiny peak over here, but this is not enough to detect an H1 line, because there are some recommendation from ITU that it has to be, the noise floor has to be below a certain level. And we started with the blue signal, which is the one over here hidden behind. And after we did all of these decomposition, canceling, we end up getting the reconstructed signal, which is the orange color. And that resembles very much like the astronomical signal. Again, there are other results that I don't want to go into details. But then we quickly realized that, well, that was a good initial start, but what can we do better? The first method had high communication overhead as well as high computational complexity. And then we introduced another version where we reduce the communication overhead significantly as well as the computational complexity. And how we do that is we utilize neural network models to reduce the overall communication overhead so that our the information that is passed from from the base station to the telescope is minimized. So there are two parts to it. So first of all, we want to compress the actual signal, the baseband signal. So we train a model, and this one we call as RFI compression model. We train a model together, which is a variational autoencoder, which takes in the signal and then creates a much smaller sample subspace. And this subspace, we will share it in real time with the base station. And it reconstructs back to the actual baseband signal. So the whole part can be trained together and is trained together, encoder and decoder part. But the job of encoder is just to compress. And after the whole thing is trained, the decoder is basically shipped to the telescope, or you can think that the encoder is shipped to the base station. And we just use simulated signal, and again, the baseband is just signal. It hasn't gone through any channel, so it's just a variety that is more important. So what we see is over here, this is going back to the base station. Now, what does the telescope, what does a telescope do with that? Telescope takes in that whole decoder that is trained together with the encoder, recreates that back, but that is an almost perfect baseband signal. That baseband signal is not much used because the telescope doesn't get that signal. It gets a signal which has propagated through the channel. It has been filterized and channelized and even quantized at the receiver, and we have to map to that signal. So then we map that signal to that through another network. We call it as mapping network. This is a full architecture of the whole thing. And this actually is showing the different parts to it, because it's not just the channel addition. There are side lobe gains. There are different filters to match the astronomical signal, as well as a telescope, because the telescope uses polyphase filter at the front, and then those filters are channelizing the signal into much smaller channels. So we have to match all of those. So the signal structure changes completely from the baseband signal. And using this model, we can see how effective it is. So we look at this. This is the current version, which is using the same overhead, which is using this much overhead, which is this version, which is the neural network version. But if we look at the previous version, which was this version, and we just stop not sending all the eigenvectors, we just send the number of eigenvectors that matches the same overhead, we can see that it cannot reconstruct anything meaningful. To reconstruct of the same quality, our overhead becomes 1.23 gigabits per second instead of 524.4 megabits per second. So you can see that there's huge amount of improvement that can be done here. There are other results that actually goes through the different model compression and other different floating point representation that we used, and how they varied our results, changed our results. So there are other works that we kept working on, which I haven't put in here. So far we considered only one base station in this work. But there are other works that we have done where we are considering multiple base stations, not just one base station around the radio telescope, but what if we have multiple base stations? How do we handle that? So we have done that in multiple ways using Karhunen-Love decomposition, as well as different neural network models, not just simply using the same existing architecture, but coming up with new, because it would, with more number of base stations, our overhead will grow increasingly if we don't handle that well, or don't come up with new thought process in terms of how to handle multiple base stations. So again, those are all there, and we can, if you are interested, let me know and I can talk about those more later on. So the next part of my talk will be on coexistence, but this one is through intelligent reflection of RFI using reconfigurable intelligent surfaces. So all the first work that we did, that was definitely motivated by the radio astronomer in my collaborator, that they are facing huge issues with the base stations. But then we also realize it's not just the base station. So we have something working for the base station. Base stations can collaborate because there are internet or wired communication between the base station and the telescope. So it is possible. However, what happens when there is a mobile transmitter or airborne transmitters? So if there is an airborne transmitter, especially in today's case, today's scenario where we have a bunch of satellites, LEO satellites that are definitely providing communication to direct to phones, signals from airplanes. So a bunch of ADS-B signals are transmitted by airplanes. So how can we handle those cases? Because we cannot just randomly collaborate over the air, because that is going to create more RFI for the radio telescope, right? So that's where we came about thinking how mobility will change the overall RFI. And here is one example. This shows the amount of flights that actually pass near Owens Valley Radio Observatory. So they cannot basically look at this side of the sky in 1090 megahertz because that's where ADS-B signals are. So what we proposed is, here is the case. This is showing a flight, but it can be, this is mostly showing an ADS-B signal transmitted by a flight, but this can be a satellite system as well. And we can find that there is a direct path that is for the RFI that is directly coming to the radio telescope. So what we suggested is, if we can place a reconfigurable intelligent surface nearby the telescope, then we can reflect and then reflect the signal intelligently towards the telescope such that it cancels the direct path in both phase and amplitude. So that was the initial thought that we had, that, well, if we do this, then that would be great. Then we don't need anything because we can create an electromagnetic quiet zone. Most of the prior work has been done post-processing, meaning after the signal goes through the whole receiver chain. That's when we do all the modifications and post-processing. But in this case, if we can cancel it before the signal actually goes to the ADC, then a lot of those post-processing can be completely removed. And there is no issues of saturation of the ADCs and all of those things. So that is what we will gain if we can do this. So yes, we can do this because we have been publishing a lot on this topic, and essentially there are few parts to it. Maybe I'll go to here. So first thing is to cancel or to reflect, to cancel exactly in phase and in opposite phase and exact amplitude. We need to know what are these angles, where is it coming from, what is the direct path, what is the angle of arrival. So that's why we place an RFI detector and estimator close to the telescope that finds the direction of arrival. And just because we know this location and this location, we can understand what is the direction of arrival here. And we place another reconfigurable intelligent surface nearby. So then we know that what is a signal coming to each of these cells or arrays, and then they get reflected to the radio telescope such that we cancel it. So the magic sauce is basically the RIS beamformer, which provides what amplitude and phase should we change for these reflectors to reflect and cancel it here. And at the very end, we have a real-time feedback to say that, oh, there is a residual RFI, and that can be used as well for tuning the RIS. So our goal, which is still partially done, not completely done, is to implement the whole process in real time. We have a 16-channel RFSoC, which is a Xilinx board with 16 input antennas, and these are placed, this is an URA, uniform rectangular array, where they are exactly separated for 1090 megahertz frequency, because we are interested in 1090 megahertz. And this is a small radio telescope, so our initial goal is to build an RIS unit with fewer number of elements, and then use that and this is actually in our rooftop in University at Albany's rooftop. It was there for a long time, and it was not used, so that's why we didn't actually buy this. We were fortunate enough to find this, and now we are in the process of refurbishing this one. So we are going to implement all of this using one dish, which is at UAlbany, and then we will finally go to OVRO for validation in a DSA 110 antenna. So how can we do all of this? So first thing is, if we have a receive power at the telescope, we can just know the receive power using simple phase transmission formula. So this can be this is known, right? Now, if we have a telescope, it will get a signal that is in the direct path, and we can write that to be a signal like this, where this is the direct path signal. This is the signal of the direct path. But we also will be able to trace or reflect from this to get the reflected path. So we have to have a reflected set of signals. And the reflected signals will be M elements of different RIS number. So we have multiple elements in the RIS, and those will be used for reflection. And this will be the total amount of signal, or the total signal that will be showing up at the telescope. But we can say that we have canceled it only when we have the summation of both the direct path as well as the reflected path. These two will end up summing to be 0. That's when a perfect cancellation happens. To do that, we need to know some of these angles, and some of these understanding is how to calculate these values. And again, I wouldn't go into the details of how we did the geometric values for each of these, but we did some numerical calculations using geometric property to understand how the element will change and reflect and how it should change. So essentially, that's what you're seeing, that every single element here is going to get reflected. And because of the distance between that, there is a path difference for every single element. And we did some, again, basic calculations using geometry to find the RIS, what should be the amplitude and phase of the RIS unit. And this was our different parameters for setup. And you can see over here, this one is just a reflected energy. So if the signal comes from this direction, then we did all the calculation at the RIS. So RIS is right here. and it is reflecting back this, where this is towards the telescope. Now, the direct signal not only comes here, but it's infinite number of rays coming to the telescope as well. So when it comes to the telescope and we superimpose those signals as well, we see something like this, where the energy field over here, this is a telescope receiver, and you can see that it is completely dark zone, which is a very low value, which means that we were able to cancel out all the signal, all the interference. One of the main components, and we are still working on improving different versions of this, because now we are actually in the process of building the RIS unit, or one element of the RIS. And we have done a lot of circuit analysis, HFSS, EMAG simulations to show how it really will cancel. This is with real circuits, with real parts to it. But there is another part to this as well. So we also need to do direction of arrival. Although direction of arrival has been done for a very, very long time, and there are several algorithms that are very well known, we still did not find enough work that really does it in very low SNR scenarios. So that's where we felt that, well, there has to be a need, or we have to work on that. So what we did is we have a 3-stage algorithm. In the first stage, it scans the whole sky in a coarse, for a coarse DOA estimation, and then we do a fine estimation, and then finally we actually do many of these, and then we many of these instances, and then we combine the signals using clustering, and we predict that the direction of arrival. So with that, I would like to acknowledge, because especially my past students and current students, my students who graduated, they do all the hard work, and I get the privilege to talk about those work. So definitely without them, I cannot run. Students that I collaborated with, many of them are not my students. My collaborators, especially for this one, without the radio astronomy person in the group, I couldn't have done anything, because I knew so less about the integrity and all the details of radio astronomy. And of course, the funding agencies, without whom we cannot do much work. So I would like to stop here and take questions.
Thank you, Professor, for your excellent